Okay, so I'm going to be showing some interesting kind of stuff. This is kind of, I guess you might say, like the world of digital cymatics. So I'm using fuzzygraph. You're welcome to go to fuzzygraph.com and you can follow along. This is an equation that we have plotted here. It looks kind of like the sun. And what it is it's actually basically 12 resonators. They actually generate sync functions for those who know what that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So equally spaced around the center. And I have, you can see what this equation looks like. It's a little bit long. Um, the way I'm playing with this though is fuzzygraph has what's called the Digital Cymatics equation generator. There's some caveats, some reasons why. There's some other features I want to add. Um, this has no concept of boundaries. So most cymatics involves having like a plate that has bounds, like edges. And a lot of times with wave patterns, um, you have things bounce off of edges and then come back and reflect and have all kinds of cool um, recursive dynamics. This current form doesn't really have bounds. It doesn't have edges. It's kind of a theoretical infinite mathematical space. But that so anyway, it's a little different than conventional cymatics. I'd like to add bounds to it eventually, but right now it's boundless. But it has some interesting patterns. So okay, so this one, I was playing with this and just before recording this, and I found some interesting behaviors. Um, and what I'm going to do is I'm going to start with these points, these resonators, all toward the center, and I'm going to expand them out, and we'll see what happens. So here with the digital cymatics generator, just to show you all how it works, this has 12 resonators at a distance of 1. Um, I'm going to go ahead and set this to. Actually, let me show you in another fuzzy graph just a little bit more about this. So let's go from scratch here and let's say 2, just all the default settings. What do we get? All right, we get something it looks like a pair of eyes, right? A distance of 2. You can see distance of 2 apart. I can I could change the rotation. Um, 1 point. These are radians. 571. It says right there. I don't remember that number. Um, rotate it right. We could notice also this kind of feature with the digital cymatics equation generator for exactly the kind of playing that I've been doing here. It kind of remembers your previous settings. So let's move this up to like 3 resonators instead of 2. So you can see a layout what this is going to look like here. Cool, right? Okay, so back over here, let's bring this to 0. What do we get? All right. They're essentially like 1 point, right? So this is actually basically a two-dimensional sync function. This would be basically the same as having like 1 resonator. And so let's expand these out. I'm going to go to 0.1. And you can actually, I don't know if you can see that on the video, but there's a little ring here. It's worth noting you can see the error here. This is fuzzy graph, so it's plotting the error instead of where is the equation true, is the equation true at this point? Yes or no? Yes or no? Yes or no? Yeah. It's how far off. What is the error if you plug this xy coordinate into the equation and get the residual if you subtract the left and right sides. Okay, so let's expand this out. Let's go to 0.2. All right, so you can see those moved out. Let's go to 0.3. You can see that little ring there of these resonators. Let's go to 0.4. Now it's kind of interesting, like you can kind of see what's happening here. There's basically the frequency of so frequency is one of the things you can set in here, right? That the frequency is here. It's a frequency of 2. Um, uh, let's see what it looks like if we set it to 4. To 4 real fast, for example. Right, doubles the frequency. Okay. Let's set that back to 2, though. All right. And so that frequency corresponds, to waves at a certain distance apart here. And it's interesting because you can kind of see whenever initially the resonators, when they were closer to the center, they were not interfering with any of these rings, or maybe actually I guess they were interfering with this one at some point. Now they're interfering with this ring, and it's just interesting. I bet if you go just, let's see, what's this distance? Let's try this actually live. I've never done this. So this point here, it's x equals 0. The xy coordinates are shown up here. So this is basically x equals 0, y equals 0.39. This is let's go to about 0.6. So let's change the distance to 0.6, and let's see. I'm guessing what's going to happen is this ring of resonators is going to be here, and there's going to be 2 rings inside of the resonators. So let's see if that's true. What do we say? 0.6, I think. Bam! Yeah, great. Exactly as expected. Cool. All right. So that's kind of interesting, right? Like we could expand out to the next one now. About 0.8. Okay, I think I see the pattern. 0.8. Oh, but now we're getting some other interesting stuff here going on. That's cool. It did do what expected. Okay, let's go. I think we know the pattern right now. It's every 0.2 about. Yes, so now let's go to a distance of 1. Actually, let's go to 0.9 and see if anything changes. Let's go right in between the wave crests. Oh, that's cool. It breaks them up, right? Oh, okay. Cool. I've played around with some stuff like this, but this is my first time kind of going through some of this stuff myself. So this is actually kind of cool. Doing math, science, exploration. Anyway, okay, cool. So our resonators are right here, and you can see this is, okay. So that's cool. Like things get more like chaotic almost when they are, you might say, out of phase with the center. And when they're in phase, when they're on a wave, like let's go to exactly a distance of 1 now, and I think things are going to be a bunch of rings now. Let's see. Oh, okay. Well, so it is a little more orderly, but now, okay, so you see the nice clean rings, and then this one, this is where it would be, but now I don't know, it's doing some cool, and now, yeah, you see what's happening. Interesting. Let's go to maybe 1.2. Cool new stuff. Let's start zooming out faster. There's something I wanted. There was a cool, interesting thing I got to after doing this. I was wanting to show. This is what made me think of doing this video. So hang on till the end. Hashtag. But let's see. Okay, let's go to 0.4, 1.4. Some cool patterns. 1.5. 1.6. I'm gonna go to 2. Some cool stuff. But okay, so you can see now at this distance. This is at 2. So the distance from here to the resonators, that's 2, as it shows up over here. Let's go to 3, and then some of these are going to go off the screen. But also a question to be asking yourself is like, what's causing this pattern to be like it is? And actually, one kind of question I had was, does it always change as you expand these toward the center? At the center, they get to a central, bunch of rings. Is there, if you keep expanding these further and further outward, does the pattern ever settle down? That was kind of the question I was exploring. Okay, let's go out to 3. What do you think? Do you think it settles down? Okay, so you can see what this looks like now. Let's go out to 4. contour. Okay, you can see this kind of around the center here. It's kind of like maybe stabilizing. 5. Yeah, this is starting to kind of look stable right here, right? Now you can see these resonators way out here. They're almost off screen. Let's go to 6. There's a few details as to why things change. Basically, the color mapping depends on the lowest and the highest points. And if you notice over here, you'll see the min and max overrides. In there, you actually can see the min and max values. So over here, the max is now 0.76. Just to go back real fast where the resonators were on the screen, that number is 42. So that's why, and I could even, make this 0.7, and it's going to have the same color scheme as you can actually. That's the point of the overrides, is you can keep really big points from blowing up your color mapping. And there's other cool ways. Sometimes you want to do that though, and there's interesting artistic things you can do with that. But let's leave the overrides off. Okay, right. And let's go back to, now let's go to 7, further out. Let's go further out. Let's see. Okay, so this has changed some. Let's go to 10. It's changed some more. Is it ever going to coalesce? Is the pattern ever going to settle down? What do you think? Let's go to 12. That looks kind of stable between there. Let's go to just 20. 20. Changed again. Now we got these kind of loop things. Let's go to 30. This is looking kind of stable here. Let's go to 40. The center's looking kind of stable, right? Let's go to 60. All right, this is looking stable. Now you see this right here. This kind of, whatever these little loops you want to call them. I think that these things stay around now. Let's see, but things further out change, I think. Let's go to 100. Yes, right. So this center is now stabilized, I think, and things out here are still changing. Let's go to now. Let's now go by the hundreds. 200. Okay, see, right? Let's go to 500. Okay, now you're seeing how, okay, now we have these rings out here that are stabilized. But now let's go 1,000. Pretty stable. Let's go 2,000. Okay, and so basically, right, this is kind of cool. It's stabilized. And this is, these points you're seeing. So one thing to note here, if you notice, let's add some zeros. So the currently, if you mouse over here, you can see the error. It's very small, and the max error on this whole screen for all points on the screen is 0.000285 right now. As we continue to add zeros, and this is basically expanding the points, the resonation points out. Let's make it a 1 in front there. This number is now smaller, this error. So it's like these waves. You see what's happening is as we expand the resonator centers, these waves are getting smaller and smaller and smaller and closer to 0. But the pattern that they create actually remains the same. Because of the way the color mapping works, it basically says, like in this case, map something near black to 0 and something of yellow near, whatever the max value is. And so because of the way the color mapping is working, you actually, even though the height, you might say, between the low and high points is getting smaller and smaller and smaller, apparently this visual pattern that's being shown is remaining the same no matter what. So like there's one other interesting thing to show that was a surprise actually though. Let's add a bunch of zeros. Okay, here it is. You see what happened there? This was kind of strange to me when I saw it. I was like, well, I've never seen something quite like that. It looks kind of blurry. Kind of strange. Okay, let's add another 0 and see what happens. Whoa, right? What happened? What's going on here? Um, and I actually haven't looked into this. Let's go back a little bit. So that was this. Wow. And then let's add. Let's make it instead of a 0. Let's go to. Let's see. This is 100,000. So let's go to 200,000. And this is again the distance from the center. All right. So things are looking more blurry. Let's go to 300,000. Kind of strange, right? Do you have any hypotheses as to what might be going on? 500,000, and we go up all the way up to like 900,000, and it's like nearly, you know, destroyed. Let's go to 800,000. I think what's happening. I'm gonna go down a little bit again. I thought it was cool around there. Yeah. I think that it's actually just a lack of precision in the computer. Um, the numbers that are being used to represent each number, I think, are getting so small that they're actually collapse. It's actually losing resolution, and that's why you're seeing that randomness. Anyway, so it's kind of cool. This is basic. So basically, in other words, this pixelation isn't part of the mathematics itself, but rather the computation that's running it. Um, that's my assumption. I recently, yeah, anyway. So anyway, it's kind of cool. You can of course reproduce this experiment yourself. I don't know if there's is this a mathematical topic? Does anyone out there know? Is there like a study of how waves interact in a boundless environment? I don't know. Cymatics is basically kind of a modern empirical study of how they react in a bounded environment. But I thought this was kind of interesting, where there's kind of this convergence on this pattern when things get far enough apart. Um, I thought that was kind of interesting. Anyway, that's it. Thanks for listening if you've been listening.